Hello guys, welcome back. Yeah, let's do the register. Could you please comment your names and I will tick these off. That's some nice reflection on my head today. Good. Alright, so Joseph, Molly, Tom. Weirdly, I can't swipe most of you in. The register's kind of decided something for you, which is strange. Yeah, check your attendance, guys, because it's being weird today. It was yesterday as well. Cool. All right. Understand. Good. Okay. Yes, we're continuing where we got to last lecture, which was halfway through this question. I think things should work more smoothly now. I've got a new computer, so everything should be a bit higher def and a bit less laggy, which is nice. All right, so could you guys just quickly refresh your brains as to what we're doing? I'm going to give you 6 marks to give you 6 marks to do 6 minutes a question. I'll give you 6 minutes to do the last 6 marks of this question again, and then we'll go through it. So a quick starter just to wake yourselves up. Could you guys do those two? So 6 marks, 6 minutes even, starting from now. Okay, so we need to interpret now. Probably reference. So, value of the car. That's my mic on. Good. Could you guys tell me what A and P were? Because I think I've lost those from last time. I didn't actually save those. Maybe I can fish it out. Um, yeah, so the value of A is the initial value of the car on the 1st of January 2001. And P is the gradient or the rate of increase in value. So I'm just trying to find out what P was last time. So I think we got P is 1.0658. Cool. So for every yeah, I think just a rate of increase in value is fine. I don't think we need to go any further than that with this one. Let's just have a look at the mark scheme quickly. Did I download this one? That's a good question. So yeah, they've gone for saying it's the factor by which the value increases each year. So factor of increase. Yeah, cool. And yeah, 24800 value initial value car. Cool. All right. Cool answer as well. Just let's sort that attendance out. Cool. All right. So the last bit, there's using a model. Find the year during which it first exceeds 100,000. So if I write down the model again, we got V equals A, which was 24,800, P, which is 1.0658 to the power T. We want to find T when the value is greater than 100,000. So I've set up my equation, and we're saying 100,000 is going to be, well, the value, which is on the right here, value is greater than 100,000. So divide both sides by 24,800. Which gives me 4.0323 less than 1.0658 to the power T. Log both sides. And then use power rule. So log 4.0323 less than t log 1.0658. Divide by that log over to there. We get t has got to be greater than 21.8. So t greater than 21.88. So t, which years are going to be during? So it looks like it's during the 21st year. So it's the 21st year after 2001. So that's going to be t is the 2022. That makes sense. Our first year, 1 year after 2001 is t is 2. When t is 1, it's going to be 2002. So when t is 21, it's going to be 2020 during that year. Cool. Those are always a little bit confusing at the end there, but yeah, good. All right. Next question then. And I think there's only 2 left in this paper. So question 13, 7 marks, straightforward looking integral. I'll give you guys 7 minutes to do it. So give this one a go. Comment if you need any help. So, addition. Yeah, good. Thanks, Rob. Anyone know what method we should use for this one? Or anyone want to guess what method we ought to be using? There is a clear method that we should use for this one. Any ideas? The parts. Will by parts work? I've not actually tried this using by parts. There should be a clearer other method. It might work by parts. Yeah, I can't see why it wouldn't, but it would. It shouldn't be your first choice. Substitution, yeah. So I would use substitution. And let's try doing it by both. It's good revision to try both methods. So we'll do substitution first, and then I'll give this a go using by parts. So a good substitution would be u equals x plus 2. So we get du dx is 1, so dx equals du. We can rearrange this to get x equals as well, so we can say u minus 2 equals x, and our limits. If we put in x is 2, we get u is 4, so u equals 2 plus 2 is 4, and u equals 2 plus 0, which is 2. So my integral would become the integral from 2 to 4 of root u times 2x. Well, 2x is going to be 2 lots of u take 2 times du. We get this. If we expand all of this, we're going to get 2u to the 3 over 2 minus 4u to the half du. So I've expanded the brackets, got our two terms there, and now we can just integrate. So if you integrate the first term, we're going to get u to the 5 over 2 times by 2/5, so we're going to get 4/5. That one. Second one, u goes to the power 3 over 2, and we're going to get 8/3 by the looks of it. There we go, 2 and 4. Put the limits in, clear some space. Oops. So we'll get 4/5, 4 to the 5 over 2, minus 8/3, 4 to the 3 over 2. Take away 4/5, 2 to the 5 over 2, minus 8/3, 2 to the 3 over 2. So working that out, we get 128 over 5 minus 64 over 3 minus, what's that, 2 to the 5 over 2? Which is 16 root 2 over 5 minus 16 root 2 over 3. Okay, this isn't looking too bad. So we're going to add these fractions together. And then we're going to look for common denominators. So 128 over 5. Take 64 over 3. Gives me 64 over 15. Minus 16 root 2 over 5 minus 16 root 2 over 15. Again, common denominator of 15. Gives me minus 32 root 2. Wait a minute. Minus there, I think. So that's going to turn into a plus. We can take out a factor of 32 over 15 to give us 32 over 15. 2 plus 2, which is what they wanted. Cool. All right, as Jack insisted it and Rob insisted it, let's do by parts. So we got 2 A terms, which is going to be fun. Okay. So the by parts formula, u dv dx equals uv minus integral v du dx. So u is LATE, so I'm going to go for 2x as u, because then that will reduce to 2, and then we've done the integral. So u equals 2x, dv dx is root x plus 2, or x plus 2 to the half. So we need to differentiate these, so I'm going to get du dx, it's going to be 2, and v, it's going to be integral of this one, x plus 2 to the 3 over 2 times 2/3. So put all this together, uv, so 4/3 x times x plus 2 to the 3 over 2 minus the integral of v du dx. So minus the integral of 4/3 x plus 2 to the 3 over 2 dx. So we just need to do that second integral, which doesn't look too bad. This is going to be alright, I think. So I've just lost the screen there. Okay, so we get 4/3 x plus 2 to the 3 over 2 minus, so integral of this, we're going to get x plus 2 to the 5 over 2 times 2/5 times 4/3. That's going to be 8/15 there for that one. Brackets, 0, 2. Hope this is going to work. You guys haven't commented anything, so I'm assuming you haven't spotted any mistakes, which is good. So we get 4/3 of 2 times 4 to the 3/3. Take 8/15 of 4 to the 5 over 2. Take away, first term is going to be 0. Take away 8/15 of 2 to the 5 over 2. Those are my two terms. All right, first one then. 4 to the 3 over 2 is going to be root 4, which is 2. 2 cubed is 8, times 2 is 16. 16 times 4/3 is 64 over 3. Take away 4 to the 5 over 2 is going to be 2 to the power 5, which is, what, 32, times 8 over 15, which is minus 256 over 15, I think. Is that right? 4 to the 2.5 times 8. Yep, cool. And that's going to be subtracting, or adding, in fact, 2 to the 5 over 2 times 8 over 15, which is 8 root 2. No, 32 root 2, 15. Cool. The first bracket, 64 over 3. Take 256 over 15 gives me, did it wrong, 64 over 3. Take 256 over 15 gives me 64 over 15. So 64 over 15 plus 32 root 2 over 15. And again, take out a factor of 2 or 30. Oh, my arm's in the way. 32 over 15, and you get the same thing. So yeah, you could use both. They both seem about the same scale of difficulty to do. Yeah, cool. Okay, last question on this paper. Question 14. Is this one. So we've got a 10-mark question, parametrics. Make a bit of space over here. There you go. Right, could you guys do this one? 10 minutes starting from now. All right. So, so for this one then, okay, so we need to show all the points satisfy this. We need to find the Cartesian, basically. So we're going to put these together. Because we've got cos double angle, we're going to need to use the sine version of the cos double angle formula. So let's write that out again. Y equals 4 plus 2, and then the cos double angle is going to be 1 minus 2 sine squared t. That is, isn't it? Yes. Been a while actually. Yeah, I think that's it. Cool. So we're going to rearrange the x1 to get sine, and then we're going to put that into this one. So for rearranging it, x take 3 is 2 sine t. The x takes 3 over 2 sine t. So the equation becomes y equals 4 plus 2 lots 1 minus 2 times, we need to square it first. So we get 2 lots x minus 3 over 2 squared. Alright, so we just need to expand and simplify this thing. So y is 4 plus, if I expand this bracket, we're going to get 2 minus 2 times 2 is 4, but when we square x minus 3 over 2, we're going to get 4 on the bottom, so that all cancels. So we're going 2 minus x minus 3 all squared, which gives me 6 minus x take 3 squared. Cool, so there's your part A. Part B, sketch it. So we got y equals, it's quadratic. It's nicely factorized. So we've got a x squared, which is moved in the positive x direction. It's also got a negative in front of it, and then it's going to be moved up 6. Alternatively, you can use your graphical calculator, but let's try and do it by hand. So I'm going to do a series of sketches for this. So we had an x squared graph. We then moved it 3 in the x direction. We then reflected it in the y-axis. Wait a minute, is that right? Reflected it in the, reflect the y points in the x, yeah. So there we go. This one. And then we're moving it up 6. So our final answer should be that one. Cool, so there's your sketch. Explain briefly why it does not include all the points. So because we are squaring our x values, we're not going to get any negative values. I think that's what we're talking about. Because the equation is an x squared quadratic, when we square it, those x values are going to sort of disappear. Oh wait, my sketch isn't. I have included all those values. Okay, we need to redo this then. So I'll keep my sketch, but we need to do some labeling. Let's draw it a bit bigger. So I think it's going to look something like this. But I need to apply that domain. So if we apply that domain to x, remember x is a sine graph that's been stretched and then moved up 3. So sine was like this. Stretch it, goes up to 2. We're going to move the whole thing up 3. So it was going up to 2. Now it's going to go up to 6. No, it's not. It was going up to 2. Now it's going to go up to 5. And it was going down to -2, but now it's going to go up to 1. Something like that. Okay, and t is between 0 and 2 pi. Well, there's pi. Oh, sorry, there's 2 pi. So our x values are only allowed to go between 1 and 5. So x is 1 is going to be my lowest value. X is 5 going to be my greatest value. So I need to get rid of some of the bits of my sketch. So none of this is allowed. None of that is allowed. And we need to work out what these y values are. So we can either put those into the yeah, I think that's the easiest way. If we put these into the y equation we just came up with, to get y equals 6, take x minus 3 squared. Well, 5 minus 3 squared is going to be 5 take 2, 2 squared, so that's going to be 5, 2 on the y. And the other point, x take 3, well, 1 take 3 is -2, -2 squared is 4, 6 take 4 is 2. So here we get 1, 2, and 5, 2. So that's what your sketch should look like for this one. So explain why it doesn't include all of the points. Well, as you saw, because of the of 0 to t to 2 pi, our domain is restricted to 1 to x to 5. And to be honest, I probably should have, because of the inequalities there, oh no, that's all right. Cool. All right, any questions about that one? It's a bit confusing, especially remembering to kind of cap the domain in this one. Okay, so then we've got another curve, x plus y equals k, intersects this curve at 2 points. So if I clear some space here. So y for x plus y equals k. We could also say that x equals y equals minus x plus k. So it's a negative gradient line, so something like that, which crosses at k. So we're trying to work out the values of k where it will cross twice. Cool. All right. Ooh, how are we going to do this one then? Obviously, the only values we're going to get are the values where it's going from. I do this. This is really hard. Can I reverse myself? Let's just. Oh my god, all this time, and I can reverse myself. Oh. Okay, so yeah, we're going down this way. So if you imagine moving this graph down, now we've got 2 sections till we get below that point there. So, oh, interesting. Might have to use tangents for this one. I think. Okay, let's have a think. So let's do a slightly better sketch before we do this. So our line, that 1 there, 1, 2, and 5, 2. Don't know where the maximum is, but we might need that in a minute. So that was 2, 1, 5. So because we've got a negative gradient, we can imagine it's like that. Right, so if the curve, got all this stuff over here now, that's annoying. Get rid of that. There we go. Okay, if this line is going to go through twice, this is the last point it needs to go through. If it goes any lower, it's only going to go through once. We can find our lower value of k. Imagine this line going through this point here. So we're going to set, what is that, 5, 2 into our equation and solve that for k. So if we put in x is 5, y is 2, 5 plus 2 equals k, equals 7. So the point here where it goes through this one, goes through this one, this is 7. So k's got to be more than 7 or equal to 7. But we need to find this upper value. And the upper value would still be there regardless, even if we still had the two tails of the quadratic, whatever it is. It's not a very well drawn quadratic, is it? Better, cool. So the other value is going to be the maximum. Wow, it might be. We need to basically solve a discriminant equation using this to find out when it crosses at 2 points, and that'll be our upper value. The discriminant won't know about this point though, because the discriminant doesn't know that we've got a domain limit on this curve. So we're going to do the discriminant, solving our equation with y equals minus x plus k, and that will find us the upper bound for what k values will work in this. Can you not use discriminant? Yeah, that's what we're going to do, Elizabeth. But the discriminant wouldn't work to find that lower root because the discriminant doesn't know about the range, and that lower root's only there because of the range. If you imagine it was any old quadratic, to cross this twice, it'd be any value less than here, and you'd always cross it. So, but because we've got, obviously, ours doesn't keep going continuously, then we can't use the discriminant for the lower root. So for the upper root then, let's say y equals 6 minus, what am I doing? So y equals minus x plus k. So minus x plus k equals, getting so badly, minus x plus k equals 6. Expand that, x squared minus 6x plus 9. So minus x plus k is 6, take x squared plus 6x minus 9. Get it all on one side. Minus x squared plus 7x minus 3, so minus k. So there's my quadratic. We're going to do the discriminant on that. And it crosses twice, so the discriminant should be greater than 0. So b squared minus 4ac more than 0. B squared, 7 squared minus 4 minus 1. Then c is going to be minus 3 minus k. Should be greater than 0. So solve that. 7 squared, 49. Take away 4 times minus 1 times minus 3 is going to be 12. And then minus 4 times minus 1, or take 4 times minus 1 times minus k is take 4k. Yep. So 49 take 12, take 4K, so we're going to get 37 greater than 4K, therefore K needs to be less than 37. So our range of K values in set notation, K is less than 37 over 4, greater than 7. Right, have a read through that, guys. See if you have any. See if you got any questions. That is quite a tricky question, that one. Cool. Right. So that is it. That's this paper done. Good. Cool. We've got a half hour left today. What I want to do is talk about modeling. Because well, we've done a bit of modeling, but we haven't done much making our own models. And then I thought tomorrow in the lecture, it's up to you guys. I was thinking we could do some actual kind of targeted revisions. So if you guys have any topics that you want me to go over again, that's what I want to target tomorrow. But you need to obviously let me know what topics you'd like to go back over. Integration? Yeah, we can do integration. So you have a think. If you let me know at the end of the lecture, that'd be really useful. For now, though, let's move on and do some modeling. Right. I'm trying to think of some data to use for this, and the obvious choice is to use coronavirus data, but I don't know whether that is too current events to use. So it's up to you guys. If you guys can think of some better data, do. But I'm just going to come up with 2 data points. You can decide they are whatever you like, and we're going to try and model them using some different models, basically. So first data point, let's have time equals 10 days, and we'll have x equals 50, and then we'll have time equals 30 days, x equals 20,000. Okay, random data points I have just plucked out of the sky. It could be anything. Obviously, t is measured in days. X could be number of particles or number of pounds. I don't know. Could be anything you like. Anyway, so we're going to try and create a model for this data. So if I write it at the top, we'll have maybe X is a bad choice for lettering because we want to talk about what's going to be the independent variable. T is 10 days. We'll go for N is 50. And N can be whatever you like. So we're going to go for 10, 50 as a data point. And we're going to go for 50, 20,000 as a data point as well. And I remember saying we got T and N. So first kind of model I want you guys to look at is just a linear model. So find a linear model for the data. Could you guys do that? Nice and easy. So I'm basically just asking you to find the equation of a line to start with. So if you do that, I'll give you 4 minutes to do that. I'm going to try a few different models, going to try refining them and see what gives us the best best data. So I want to say 5 minutes. I meant 4 minutes. So 4 minutes starting from now. Okay, so yeah, find a linear model. So we are just going to treat it as 2 points on a line, work out the gradient, work out the intercept. So gradient 20,000, y2 take y1 d divided by x2 d take 10. which gives me 19950 40, which is a very big number. Gradient of 498.75. Okay, so we use 1 point, so y minus 10, no, y minus 50 even, equals 498.75. X take 10. You get y equals 4.875x. Take 49375. So that would be my linear model for this data. So I'm assuming that the data starts here, ends up here, and we're assuming a straight line like that. It's very steep, very, very steep. Cool, so I'm going to leave that, so I'll leave that there. No, I'm going to write it really small at the top. So give me a sec while I do that. There we go. All right. And to be honest, I've used y and x. Let's use n and t. So n was that times t minus 4957.5. Okay, we do the same thing again, but using a different model. So, and now I want to look at an exponential model. And I would like all of you guys to try this and to put some comments in the comment section. So, find exponential model. Gonna give you slightly longer for this. If you need help, comment and I'll give you a hint. But give it a go if you want to find an exponential model. So it's going to be some kind of exponential equation that fits those two data points. So 5 minutes, I think, this time. Start seeing now. Cool. How did you all get on? Anyone get anywhere? So the key for this one is kind of starting with a blank exponential. There's a few ways you can do it. I think the way I always prefer is to say y equals e to the x, or in this case, n equals e to the t. Obviously, that's not going to work though, because we know an exponential graph looks like that. We need to kind of force this to fit our two. Imagine they're there and now our two data points. And the way we're going to do that is to kind of squash it and stretch it. We don't want to move it up or down. I mean, we could, but I think easy way is just to try and force it to meet those 2 points. So we're going to introduce a constant out the front called a and a constant at the top called k. That's the idea. So by doing that, we can now find two different exponential equations, solve them simultaneously to find a and k, and find an equation that fits our two data points, which is also an exponential. So to do this, we're going to say 50 equals a 10k, and we're going to say 20,000 equals a 50k. We're going to solve these simultaneously. Now to solve these, we're going to divide them, because if you divide them, the a's will cancel out and we'll be able to find k. So we're going to do this one divided by this one. So we get 20,000 divided by 50. Because the a's cancel, so we get e to the 50k divided by e to the 10k. And when you've got powers like that, you can just subtract them. So we get 20,000 over 50, which is 400, equals e to the power, for 50k take 10k is going to be 40k. We can then ln both sides to get ln 400 equals 40k. The k is 1 over 40 ln 400. So if we put it all together, all right, that's that's only k. We need to find a as well, don't we? So choose either point. So I'm going to use top 150. So a e to the. I'm going to type this in. It's not going to be as exact, but it'll be a lot less messy. So 1 over 40 times ln 400 is 0.148. T. And I know t was 10, so I'm going to put 10 here in some brackets. We can use that to find a. So times that by 10, put it to the power e, so e to the power I just got. And then 50 divided by answer should give me a pretty exact value for a, so I get a is 1.11. So my model would be n equals 1.118 e to the 0.1498 t. So there's my exponential equation linking those 2 points. So we've got 2 models so far. I'm going to write this one at the top as well. So this one was n equals 1. Ooh, time for one more, I reckon. So we're going to try a log to linear form model, or a log model. So we're going to assume an equation. Actually, should we do that? No, let's try something. What should we do? I can't decide what to do the last 10 minutes. Let's just look at these 2 models actually and compare them. So we got n is 498.75t minus 4957.5, and we got n is 1.118 e to the 0.1498t. It's two vastly different models. What I want you guys to do is try and predict n when t is 60. I'll see what both models predict, and we'll have a look at the differences between the models and see if we can decide which is more realistic. Cool. 3 minutes to do that because we are running low on time. So 3 minutes, give it a go. Can't hear you. Sorry, guys. I did the first one. I think the second one's wrong. 3 minutes before the end to discover that. That's a pain. Damn it. What did I do wrong? How did I do that wrong? All these questions and more. There's not much time to do this. Okay, I'm going to scrub this out and try and fix this. So what did I say? I said 10 days was 50 and 50 days was 20,000. We said okay, real quick, let's solve this because I made a mistake. 50 equals what did I do wrong? Still looks the same, doesn't it? Learn both sides. Learn 400 divided by 40. That should be a K, not a T. The K is... That's what I said. Okay, put that back in. All these should be Ks, we're doing. So 10 times that. That answer gives me 87. Okay. 50 divided by that gives me a 0.571. Okay, I think that is different. 1 minute, just about there. So my model becomes n equals 0.571 e to the 0.1498 t. And we said t is 60, so real quick, 0.571 times by e to the power 0.1498 times 60. Cool, so we get n. That's even worse. What's going on? Sorry guys, we have to leave this one. So what do I do? 11.18 instead of 1.18. Oh no, what did you get, Grace, for the original model? Because I've doubted myself and lost everything. So was it 11.18? No, I think I typed in 1.18. Should it have been 11? Did I read it wrong the first time round? For A, okay. So you think it should be that? It does look more promising. Let's give it a go though. That does look better. So we got for that model n is 89,511.9. Cool. Okay, yeah, I made a decimal place error. That's relieving. Okay, so you can see two different models. Using the same data points, we get vastly different estimates. Which shows why extrapolation is bad, because we don't know if it's linear. We only have 2 points. For all we know, it could have been... Cool. It could have been a sine wave. It could have been something like this. Yeah? You don't know what model's like, just based. Could be linear, could be exponential, could be logarithmic. Any of these models could describe those points. That's why we often need a third or fourth or fifth or sixth or seventh. The more data you can get, the more you can be confident about your predictions. Okay, so yeah, Ollie said integration is. If any of you want me to look at any other topics, comment now. But I'm happy to look at some integration techniques tomorrow. Look at some integration questions. Cool. All right, take it easy, guys, and I will speak to you tomorrow. Cheers.